about these. I think we'll cover each one of those, but they are pH, turbidity, temperature, and then any reducing compounds that might be in the water. Of note, when we talk about, we'll talk a bit more about cryptosporidium, but so that it's kind of difficult to treat because there's this cyst that forms around the organism. It's a protective shell, and it makes it difficult to affect it with chlorine. So there are three main primary disinfectants. The most common is chlorine. It's effective against bacteria and viruses, and most of the protozoa if it's given enough concentration and time. Those two things that are most important. It also is great because it has a lasting residual. We'll find that some of these others don't. And each one of these has its pros and cons we'll discuss here. Chlorine, one of the cons, it's not effective against cryptosporidium, and it can produce disinfection byproducts. Disinfection byproducts will be discussed as well, and that they can be problematic. The second primary disinfectant is ozone. That's created by passing oxygen through an electrical discharge, and it converts the O2 or into ozone or O3. It's a powerful oxidizer, and it can kill all three of the different types of microbes. Now, some of the downsides to ozone, it's got a relatively short residual, only 8 to 20 minutes. It can produce a little different disinfection byproduct, bromate. It can produce that if the water contains bromide. And then the third kind of disinfectant is UV light, and that's it's pretty effective. However, there is no disinfection, or there's no residual at all with UV light. And so this slide here, we're going to discuss, or it'll show us some of the importance behind chlorine disinfection. So when we look at this, it shows the number of deaths per 100,000 people, starting back in the 1900s. As you can see, there were considerable number of deaths early on, and they've become fewer and fewer. We had thousands of deaths. And a lot of this was because of different things that we learned through time. And in the 1670s was the first time that we were able to see microbes under a microscope. So that before that, there was no reason to suspect that there were things that small. In 1854, John Snow did some groundbreaking investigation and in London at the Broad Street pump cholera outbreak. That's a really interesting story. I encourage anybody. I believe there may be even a book written about it. But that was another one of these important discoveries through time. In the 1860s, Louis Pasteur created the germ theory, and the idea is that these microbes that we were able to finally see in the 1670s, they were causing the disease. So, and then in 1908, in Jersey City, New Jersey, the first water system in the U.S. began chlorinating the drinking water. So from 1908 until 1945, we can see the significant change in a reduction in the number of deaths related to typhoid fever, down to the point where in 1945 it was less than 1 death per 100,000 people. So this next slide is one of the more important things in my mind. It's something that I think we all need to pay a little bit of attention to. This curve shows us the effect of adding chlorine across the bottom and what effect it has on chlorine residual on on the top, on the left side. You'll notice the curve starts up, goes down, and then continues up. And so in this blue area, we're adding chlorine, but we're not seeing any increase in chlorine residual. And that's because there's these reducing compounds that are taking up all the chlorine that we're adding. So we're adding chlorine, but we're having no effect in our chlorine residual. And in the green area, we're starting to see an increase in our chlorine residual, but it's forming chloroorganics and chloramines. And that the problem with chloramines is that they are the ones that give that chlorine smell to the water. And so if you're operating a small water system and you start applying chlorine, you'll continue to get complaints. And so as I would go out to water systems and try and promote the idea that they need to increase their chlorine application, it became difficult because they felt like all they were doing is getting more complaints. But as you'll see in the next area, the chloramines are destroyed by the additional application of chlorine, and that reduces that smell component that everybody complains about. And we'll get to this point where it's called break point, where at that point we don't have we're not losing any of the chlorine that we're applying. As we continue to apply it, we continue to see residual. So it's an important thing. It's very counterintuitive. It becomes difficult to tell people that, just stick with the plan, continue until you'll see the dividends. Get to break point and it'll start to get better. So that's something I really like to stress with people. It's an important thing. So that area below the break point, that's considered combined chlorine. And then the stuff above it is the free residual. So this is just another thing another slide that can show us that we've got free residual and we've got combined residual, and the total of those two is the total residual. So let's look at an example. A dose of 1.5 parts per million chlorine is added to water, resulting in a measured free residual of 1 part per million and a total residual of 1.3 parts per million. What is the demand from the reducing compounds? All right, so we know we have one part of free residual. We've got a total of 1.3 residual, and we had a dose of 1.5. So how do we find that? So if we take the 1.5 from what we dosed and we subtract out the total residual, which is the sum of the free and the combined, that'll tell us what our demand was. So in this case, it's 0.2 parts per million. So our chlorine dosage is equal to our free residual plus our combined residual plus our demand. All right, so we're going to jump right into our first poll. Keep in mind, we've got this information that we just covered. Poll number 1, a drinking water with a demand of 0.4 parts per million has a total chlorine residual of 1.7 parts per million. What was the chlorine dose? All right, Scott, if you can put that poll up, we'll give everybody a minute or two to respond to this one. We'll go through and discuss why we have what the correct answer is and why. All right, we're at 80% of the participants responding, so I, at this point, won the poll. Hopefully, everybody's had a chance. And I'll share these results. So, the results, well, 90% of the respondents said that it's 2.1 parts per million. 8% 1.3, and 2% 1.4. Nobody said that it was 5.7 parts per million. So let's look at this. So we have our total chlorine residual of 1.7 parts per million. We have a reducing compound demand of 0.4 parts per million. So our dose is going to be equal to a reducing compound demand plus our total chlorine residual. That's our free and combined. And so we get an answer of 2.1. So I guess the majority had the right answer. All right, so we're going to talk a little more specifically about the different types of chlorine. So there's three main types of chlorine. There's a solid, liquid, and a gas. And from this slide, you can see kind of the layout of a gas chlorine system. These tanks, and the tanks produce a gas, gets put into the water stream. And this should look familiar. We talked about the pounds formula, and pounds per day is equal to the million gallons a day flow times the parts per million dose times the weight of water per gallon. This just shows you kind of what a rhodometer, a gas feed regulator, looks like, and that's how we know how many pounds. That's our feed rate for gas chlorine. That's how it's set up. So we'll go into a little bit of an example for gas chlorine. What is the feed rate setting for chlorine gas in pounds per day if the plant flow is 1.2 million gallons a day and the dosage concentration is 1.5 parts per million? So for our solution, we're going to plug in 1.2 for the flow, 1.5 for the dosage, and the weight of water per gallon doesn't change. So if we look at that, 1.2 million gallons a day multiplied by 1.5 parts per million and by 8.34 pounds per gallon, we get 15 pounds per day. So the pounds formula can also be rearranged. So I think we did a little bit of this yesterday where we moved our formula around. So if we decide we want to determine the dose, we can do that. So we, in essence, divide both sides of the equation by the million gallons a day and the 8.34 pounds per gallon. What we'll see is we're going to cancel the flow and the weight of water per gallon out. And then it's going to give us a formula that has a dose is equal to the pounds per day divided by the flow times 8.34. All right. So I said before, there's certain formulas you may want to jot down when it comes to polls. I'm not saying that that is one or it isn't, but maybe you may want to write that down. So now we're going to do, we're going to look at what it's called. I've heard it called the pie formula. I've also heard it called the picnic formula. It's just another way that people learn how to do these types of problems. So we're going to cover this as part of the pounds formula. So in this pie formula or picnic formula, you multiply the thing on the top is equal to the multiplying all the things on the bottom together. So that's basically our pounds formula. So we got pounds per day is equal to million gallons times the dose times the 8.34 pounds per gallon. So in an example, taking an example, we want to calculate the gas chlorine feed rate for a plant with a flow of 0.6 mgd and a dose of 0.9 parts per million. So these numbers go into these spots on the pie formula. And so we take our 0.6 mgd, multiply that by 0.9 milligrams per liter, times our 8.34 pounds per gallon. And we get an answer of 4.5 pounds per day. All right. So if we decide we want to use that same pi formula and we want to solve for something on the bottom, we can do that. So in our example, we're going to calculate the dose if gas chlorine feed rate is 4.5 pounds per day and the plant flow is 0.6 million gallons a day. So we're going to work this thing kind of backwards. And so what you do in this case is throw those in, and our dose, it could be any one of these things. We could put that on one side, and then on the other side, we're going to have the top divided by the other two things. So in this case, we're looking for dose. So we take our feed, put that on the top, and we divide by the sum or the multiplication of the flow and the 8.34. It's pretty much the same formula that we had talked about before. It's that the dose equal feed in pounds per day divided by the million gallons a day times the weight of water. So the answer is 0.9 parts per million. All right, so that was quick. We're already on to our second poll. So our second poll, an operator checks the settings of a treatment plant and notes that the gas chlorine feed rate is set at 30 pounds per day and that the plant flow is 2.1 million gallons a day. What is the dose of chlorine in parts per million that is being administered to this water source? All right, Scott, can you, you've got the poll up. Let's set a timer for 2 minutes, please. Thank you. So it looks like we've got about 3/4 of the people have responded at this point. So I will end the poll. And if you'd like to, you can put your answer. If you didn't get a chance to put it in here, you could put it in the chat. So we end the poll and share the results. So we have 84% of the respondents said 1.7 parts per million. And 6% say 0.58 and 4% say 1.5. Let's go through and we'll look to do the solution to the problem here. All right, so an operator checks the settings of a treatment plant and notes the chlorine feed rate is set at 30 pounds per day and the plant flow is 2.1 million gallons a day, what is the dose of chlorine in parts per million that is being administered to this water source? So our dosage formula is pounds per day divided by flow and 8.34 pounds per gallon. So these things would fit into these slots for the pi formula. And that simply becomes dose is equal to 30 pounds per day divided by 2.1 million gallons a day and divided by 8.34 pounds per gallon. So that gives us 1.71 parts per million. All right, great. I believe that's what the majority said. All right, so the next type of chlorine that we're gonna talk about is the solid form of chlorine. It's called calcium hypochlorite. It's also described as high test hypochlorite or HTH. Now, when we look at that, it's a little different because as you see on the bottom, calcium hypochlorite can be found in the form of tablets, which I've heard often referred to as pucks. It can be in the form of pellets or a powder. And note that it's generally, it comes in strengths of 65 to 70%. So that's different because we had always, with gas chlorine, we had 100% available. So when we're going to do the pounds formula for HDH, we need to take into consideration the strength. What's the strength of the HDH? And so the top part of the equation calculates the pounds of pure, and then the bottom part of the fraction here is going to identify the strength, and that's going to take into consideration that'll even things out, and so that we'll be able to work this formula out. So we make sure we have it. And this HDH is quite often the stuff that's used in to shock pools. So we're going to do just disinfection with HDH. We've got a little example problem here. We have how many pounds of 65% strength HDH are required to disinfect 0.6 million gallons of water with a total residual of 1.5 parts per million. So using that formula for calcium hypochlorite, we're going to say that we're going to put in our pounds of HDH are equal to the 0.6 million gallons of water times the 1.5 parts per million, our total residual, times the 8.34 pounds per gallon, the weight of water, divided by 0.65, because it's 65% strength. So when we do that, we'll get 7.506 pounds over 0.65, or 11.5 pounds of HDH. So you'll note this top part, the 7.506 pounds, that's how much we would need if we had gas chlorine. So because it's not all 100% available, like it is with gas, it's only 65% available. We need more pounds of it to make up for the difference in the strength. So now we're gonna go from the solid. We've covered gas, we've covered solid. Now we're going to talk about liquid.
We do have a question in the chat about
Yes.
what about the amount used?
So the amount used is we're going to take when we look at that, I mean that is 11.5 pounds of the HDH. So the amount we use is going to be that we're going to weigh it out at 11.5 pounds, and we're going to put that was only the residual. All right, I'm not sure. So we're creating a total residual of this. I'm not exactly sure what we're getting after. Maybe I'll take that up after the session. All right, so we're on to specific gravity. So when we're dealing with any kind of liquid with water treatment, we need to make sure that we take into consideration the specific gravity. Now, when we So the weight of water compared to the weight of a substance, that's the specific gravity. So we know that water weighs 8.34 pounds per gallon. And it is the basis for all the rest of the specific gravity. So its specific gravity is 1. So when we look at liquid chlorine, it may have at 12.5%, it may have a specific gravity of 1.2, which means that it's 1.2 times heavier than water. So now we have to take into consideration that it weighs more than water, and now we're looking at liquid chlorine has a different concentration as well. So we take our 1.2, our specific gravity, we multiply that by the weight of water per gallon, and that gives us the 10 pounds per gallon. So it's going to change our pounds or our gallons our formula here. So when we're looking at liquid chlorine, we have an entirely different formula. As you'll note, the top is the same, and we're going to take into consideration the percent strength, but the weight per gallon is also going to change on us. So that top part of the equation, that calculates our pure pounds of pure chlorine. Once again, as if we were using gas chlorine, we wouldn't have to take into consideration the stuff at the bottom here. We've got our percent strength. In this case, it's 12.5%, or we're going to put in 0.125 in that point. And then we're going to have to take into consideration the specific gravity and the weight of water here in our calculation. So as we said before, if we have a specific gravity of 1.2 for liquid chlorine, we could just put in the 10 pounds per gallon in place of the specific gravity times 8.34 pounds per gallon. All right, so we'll look at an example for liquid chlorine. What is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 500,000 gallons a day and the dosage is 0.9 parts per million? Use the following formula and plug in the values for flow, dosage, specific gravity, and solution strength. All right, so this is the formula we used previously. So our flow is 500,000 gallons a day. Our concentration is 0.9 of a part per million. The weight of water per gallon is here. We've got our percent strength, 12.5, comes up to 0.125. Specific gravity of 1.2, and then the weight of water. Multiply across and divide, and we get 3 gallons per day. So this is an example of one of the common pumps that's utilized for adding chlorine, especially for small systems. It's considered a positive displacement type of pump. You'll note that we've got, there's 2 dials on here, one for speed, one's for stroke. The speed is how quickly the pump operates, and the stroke is how much chemical is added each time it operates, or the stroke goes through. So we look at this, the information off this pump is on this little tag. It's given us a max flow of 0.58 gallons per hour, as long as it's within a PSI of 250. So that's the maximum occurs when both the speed and the stroke are set to 100%. So we're going to look at an example with this pump and see let's find out what our actual output would be if we had set, if we take our 0.58 gallons per hour pump max, and we set both the stroke and the speed at 70%. So the max output is going to be, we're going to take that and we're going to multiply by the percent of the stroke and the percent of the speed. In each one of these cases, we're going to use 0.7 for that. So we take our 0.58 gallons per hour, multiply by 0.7 for the speed and 0.7 for the stroke. when we do that, we get 0.284 gallons per hour. Okay, so 0.284 is a little less than half, very close to half of the max output of the pump, which is a good thing because if we've got a pump that can operate at its halfway point, then that means that we have room to increase and we have room to decrease. So that's a good, if I were trying to spec out a pump and we typically had a flow we needed a flow of 0.284 gallons per hour, this would probably be a good pump to utilize. Now, what's the output in gallons per day? We can just take our gallons per hour, multiply that by 24 hours a day, and that'll give us our gallons per day, in this case, 6.82. This calculation compared to the sodium hypochlorite feed rate calculation. So next we're going to look at disinfection contact time. So we talked about how important it is to have that time that we have for the chemical to be in contact with the water. Concentration and contact time are important things, right? So theoretically, our detention time is equal to the volume divided by the flow. Now, in real world, it's probably not going to be that high. It's going to be something less because there's definitely an opportunity for short circuiting or the water not being in contact with the chemical as long as it appears. So we put in a baffling factor. So if we've got a good baffling, and I'll show a slide that helps with that a little bit of the next slide, that's going to give us more time. So in this case, we're going to say that the time is equal to that volume in gallons and multiplied by the baffling factor and divided by the flow in gallons per minute. So we look at this slide. This shows some good baffling. So the idea is that the water has to flow through all of this. So it takes a long time to get from point A to point B. And the second, the one on the right here shows areas where in red where there's going to be higher velocities and in blue where there's lower velocities. So this whole idea of how something is short circuited, the red is going to spend little time and the blue is going to spend a lot of time. So ideally we have something where we have baffling. And this table just puts some information that associates with what the baffling factors might be. So this is an example of where you've got very little baffling because the water comes in at this point and it could potentially just go straight here. It could just short circuit, not spend a good deal of time in our tank. So that would be something that would be in the unbaffled to poor range. If we've got a baffling that's similar to this, where it's got to go through all of this, it's likely to be in the average to superior range. And you see these factors, the factor is less for when we have less baffling, and it's more when we have more baffling. So we can work a little example of that. What is the disinfection contact time for a tank that has a volume of 75,000 gallons and a baffling factor of 0.5? The flow through the tank is 500 gallons per minute. We've got 500 gallons per minute going into the 75,000 gallon clear well. So our solution, we take that, our contact time is going to be equal to the volume in the tank times that baffling factor, and then divided by 500, the 500 gallons per minute, the flow that's going through there. So you can imagine, I mean, we'll do this answer, but if this number is higher, that means we're going to have a larger number on top. And if that number is lower, it's going to have a lower number on top. So that definitely affects our answer. If that answer was 1, we'd have, 150 minutes worth. So in this case, it's 75 minutes worth of contact time. All right, so why we're talking about all this contact time, and that's important because these, we need to come up with what they call CT values, and we need to have log inactivation as part of our surface water treatment. So the surface water treatment rule, the requirements for inactivation and removal for Giardia and viruses, there's 3 log for Giardia, and there's 4 log for viruses. So that means that 99.9% of the Giardia needs to be removed throughout inactivation and removal. And then for viruses, it's 99.99%. And the reason that Giardia only requires 3 is because it tends to be a larger bug, and it's easier for it to be removed through the process. Viruses tend to be more resistant to filtration due to their small size, and they're also more resistant to disinfection, so that we have to be more protective of the viruses. So the combination of filtration and disinfection must achieve these removal rates. And notice we're going to get some from our filtration, we're going to get some from disinfection. So what are some of the considerations we have to have? We have to make sure that we've got multiple barriers. We've talked about this before. Having multiple barriers that are good. Start with source protection, filtration, testing. These are all different barriers. We can't just add as much chlorine. We can't add a ton of chlorine necessarily, because we could cause the formation of disinfection byproducts. We need to meet all the specific requirements. It could be that the state has state-specific requirements that are above and beyond what are in the surface water treatment rule. And then we need to keep in mind that the design of our plant can affect how many credits we get for removal. So this is a CT table for 4 log inactivation of viruses with the addition of chlorine. One thing I want to note on here is that these are the temperatures, and this is the amount of time that's required. So you can see that at higher temperatures, there's less time required. So that's just indicative of the fact that chlorine is more effective at higher temperatures. So on this table, we're going to match the daily minimum temperature from this column with the daily maximum pH, these 2 columns, and it'll give us an active inactivation that we're looking to achieve. So in an example, the water is 16 degrees. So we're going to go, and we've got a pH that's 7.5. So our pH is in that range from 6 to 9. So that means we're in this column. And our temperature, we're going to go with the next lower temperature. So we go from 16 into this 15 range. So that tells us that we need to attain a CT value of 4 or greater in order to satisfy our 4 log inactivation of viruses. All right. So we can do a 4 log virus inactivation problem. In this example, we've got a small groundwater system that maintains a minimum free chlorine residual of 0.8 parts per million. Contact time is provided by a 3,500 gallon pneumatic storage tank. The baffling factor of 0.3. The maximum flow through the tank is 200 gallons per minute. Determine if the system is attaining sufficient CT for 4 log virus inactivation when the water temperature is 16 degrees Celsius and the water pH is 7.5. So the first thing we do is we determine what is the contact time. So remember that the time is going to be equal to the volume multiplied by that baffling factor and divided by the flow. So we do that calculation, we get 5.25 minutes. The next thing we're going to do is calculate the CT that's being attained. All right. In order to do that, we're going to take our minimum free chlorine residual of 0.8 parts per million, and we're going to multiply that by that contact time. And that gives us 4.2 milligram minutes per liter. Now we need to compare that with our table here. So if we do that, we're in the And we have a pH of 7.5, so it falls in this column. We have a temperature of 16 degrees, so it falls on this row. So that gives us required inactivation of 4. So required CT for this pH and temp is 4. Actual CT is slightly greater, therefore CT for log4 virus is met. And I had mentioned before that pH is one of the things that had an effect on disinfection. So this table shows how that happens. So the hypochlorous ion percentages are on the left and the hypochlorite ion percentages are on the right. And you'll note that if we're going to have one or we're going to have the other. And the hypochlorous is more effective in doing what we need it to do than the hypochlorite. So if we look at a pH of 7, which is neutral, at that point we're getting about 80% hypochlorous acid and about 20% hypochlorite ion. So at that point we're getting a good amount of what we want. As the pH increases, we end up with more hypochlorite, so it becomes less effective. So it's more effective at lower pHs than it is at higher pHs. All right, so we're going to look at now we're going to look at the Giardia inactivation table. The first step that we need to go through is we're going to measure the free chlorine residual at the end of the disinfection process. So at the entry point to the distribution system. And then we're going to measure the temperature and the pH at the same location. And then we're going to choose the table that matches the temperature using the next lowest for temps in between. So for instance, we've got we're looking at a pH of 7 and we have a chlorine concentration of 1.2. That puts us right there at 76 to get 3 log inactivation. So we'll cover a Giardia inactivation problem. We've got a flow of 800 gallons per minute. It's entering a 75,000 gallon clear well, and it's got a baffling factor of 0.7. The water at the entry point to the distribution system is chlorinated, and it has a free residual of 1.2 parts per million. The minimum water temperature is 15 degrees Celsius, the maximum pH is 7.0, and the minimum free chlorine residual is 1.2 parts per million. Determine if the system has sufficient contact time and residual to achieve 3 log inactivation of Giardia. The first thing we want to look at is we want to determine what our contact time is. So we're taking our 75,000 gallon clear well, we're multiplying by that baffling factor of 0.7, and we're dividing by the flow of 800 gallons per minute, and that gives us 65.6 minutes. That's how much contact time we have from the beginning to the end of the clear well, all the way through here. The exit. So our CT is going to be the free chlorine residual that we have, 1.2 parts per million, multiplied by that contact time of 65.6 minutes, and that gives us 78.7 milligram minutes per liter. Next, we want to compare that to the 15 degrees Celsius Giardia table. All right, so we pull up that table. And it is the 15 degrees Celsius table. Our pH is 7.4 or 7.0 maximum. We need to have a 3 log removal or an activation, excuse me. And we have a free chlorine residual of 1.2. You can see we're dialing this in, and that's going to leave us as a CT required of 76 milligram minutes per liter. So we calculated it out to be 78.7. So since what we're calculating is more than what's required, that means we've exceeded the minimum requirement and therefore we are in compliance. Always important. So we can also determine how, I guess, how much over or what in comparison what we are to what's required. So we can take our log removal of 3 and we multiply that by the CT that we achieved and we divide it by what was required. And so if we put those numbers in, we're at a 3.1 log removal when we needed to be at 3. And that's only through inactivation. So our treatment is going to give us some removal itself. And so we're going to combine the removal and the inactivation to meet our requirements. So it's not just on inactivation or disinfection. All right, so we're going to go in, we're going to look at a conventional water treatment and that plant that has a removal credit of 2.5 logs. So the state primacy agency has said, all right, your treatment is good for 2.5 logs for removal. So that means we need an additional 1/2 log of inactivation. So our disinfection needs to get us a 1/2 log so that we can get up to our total required 3 log removal. So what CT do we need to achieve with disinfection? If the temperature is 15 degrees Celsius, the pH is 7.0, and the residual is 1.2 parts per million. All right, so we're looking at the right table. We've got the 15 degrees C. We need a 1/2. Our pH, so our pH is 7. We need a 1/2. Our residual is 1.2. So we look at that. Our 1/2, our 1.2, we're in this right part of the table. So that tells us that we need 13 milligram minutes per liter to achieve through disinfection. So that inactivation portion at a 1/2 a log needs to be 13 minutes. And that'll give us the 2.5 that we get from our treatment plus the inactivation gives us the 3 log that we're required to get. Now, one of the things that we may encounter is that there will be plants out there that chlorinate in a couple of different spots. We look at this example and they're chlorinating prior to the treatment train. I actually know systems that due to things like zebra mussels, they actually chlorinate in the water at the intake. They've actually got chlorine lines that go out into their intake so that they can put chlorine there. So, and that intake line might be a mile long. So you can imagine there's quite a bit of contact time going on in those situations. But the point of this is that it can be done in 2 different places, which means that we've got one inactivation, we're calculating CT for 1, and then we've got another one that we may be calculating CT for. So it's the inactivation is the combination of both of these. So if we've got 2, the benefit we have is that we can combine them to see if we meet our requirements. The downside is there's a higher potential for creating disinfection byproducts. All right, but what are disinfection byproducts? So they're made up of 2 main compounds. There's total trihalomethane, which are these 4 different compounds. They lump them together and they consider them to be total trihalomethane. And those are problematic because they can pose a cancer risk if they're at elevated levels in comparison to a locational running annual average. And that the idea being that these samples are collected out in the distribution system at the same point, potentially on a quarterly basis, and the last 4 quarters of results, we average those and compare them to that MCL of 0.08 parts per million, and to determine whether we're in compliance. And same thing is done with the other set of compounds, the haloacetic acids. These are those 5, and they're weak acids that also pose a potential cancer risk if that locational running annual average is above 0.6 parts per million. And these things are, they're just, water just, they naturally has these organic matter in it. And, you know, if we can filter them out, that's better. But they're found in just about all surface waters at some levels. So now we've got poll number 3. A 30,000 gallon clear well with a baffling factor of 0.7 has a flow of 500 gallons per minute passing through it. A chlorine dosage of 2 parts per million is required to achieve a free residual of 1.7 milligrams per liter at the entry point to the distribution system. What CT value is being achieved in this clear well? Give everybody about 3 minutes, Scott. Okay, I see we've got about 60% of the people responded. We'll give another minute or so for those of you who would like to get your response in. Okay, we've got over 70% of you all have been able to respond. We'll end the poll here. So. What is our CT value? What CT value is being achieved in this clear well? Let's go and go through this problem. So first thing we're gonna do is we're gonna determine what our contact time is. So that's the volume of our clear well, multiplied by our baffing factor and divided by our flow. So that gives us 42 minutes for our CT value, or our time rather. And so our CT is that 42 minutes multiplied by the chlorine free residual, which is 1.7 parts per million, and it gives us 71.4 milligrams minute per liter. And this is at the end of the disinfection process. So when we measure that residual, we want to make sure that it's at the entry point in the distribution system. All right, so the next type of disinfection that we're going to look at is UV disinfection. So that's where water goes through this unit. It goes inside here through this pipe, and the UV goes on the outside. This pipe in the unit center puts out UV light, and so that the wavelength disrupts the genetic material of the microorganisms. And that's how we end up treating for these contaminants, these pathogens. Now it's quick, it does a good job, but the main problem with it or disadvantage is the fact that there's no residual. So once it leaves this, there's nothing to continue to do work on that water. The disinfection only occurs during this little area. Some of the other problems is that UV lamps, they have a limited lifespan, so they can be kind of expensive and they need to be replaced. And also it needs to have very clean water so that the light can get through to all the organisms that might be in the water. If you're interested in UV disinfection, there's a guidance manual here. Please encourage you to go to that link and check out what EPA has to say about it. So these are some estimated times just to give an idea of how long it takes for the inactivation of microorganisms through UV. You'll see that, with this dosage, E. coli is less than half a second. Hepatitis B virus is very quick. I mean, these all occur in a relatively timely manner. Now, I preface that this table shows for this wavelength, but typically the wavelength that you will see for UV dosage is slightly higher than this. But what does UV do for us? It expands the range of disinfection. So, typically with chlorine, we're really good with all of these microbes, but we're not real good with crypto. So UV can expand. It does well with all of them. So because it can penetrate the shell of crypto and deactivate it. So we can't just get by with UV. We're gonna have to add chlorine regardless. So where in the treatment train would we add UV? So if you look here, we've got our source, we've got our coagulation and rapid mix. We do flocculation and sedimentation, filtration. Well, we typically drop that in after filtration and before our clear well. So that's where UV disinfection typically happens, and that makes sense because we said it needs to have pretty clean water. So the cleanest water we're going to find is going to, all the treatment that's done prior to that cleans the water up. And then chlorine disinfection is going to happen prior to the clear well and off to the distribution system. So There are some different things that need to happen, in order for UV disinfection to take place. And we can't have too much turbidity or suspended solids, because as we said, that can hide the microbes from the UV light. So we've got a turbidity requirements, suspended solids requirements. Iron and manganese can also follow that sleeve that the water goes through. So that can affect how well it works. And then you can have some corrosion if you've got a pH below 6.5, and you can have some scaling if you've got a pH that's higher. So it's limited. The use of UV can be limited. And the third and final way that disinfectant process that we're going to talk about is ozone. Ozone's powerful. It's a good disinfectant. It can kill a lot of these organisms, including crypto. And it can also oxidize iron and manganese, which is a good thing. It can destroy those disinfection byproduct precursors, the things that can result in disinfection byproducts. It's really good for eliminating taste and odor issues, and it can improve our coagulation and flocculation. One of the things about it is that it tends to be very energy intensive, which hinders its use. How is ozone produced and fed? Oxygen's passed through a high voltage electric field, and it splits the O2 molecules into single atoms, and these individuals collide with other O2s to form O3s. So we can see here that example of the diffuser that is used here on the right. On the left, this is a bubbler system. There's a bubbler system also. We have a diffuser and a bubbler system to get this out. Another thing the problem with these is the space that it takes up. I mean, imagine this. We've got to have all of this just to treat this water. It can be kind of space intensive. So if you don't have a big footprint, it may not be for you as well. So the oxygen ozone cycle. So we start with our oxygen, we add energy, it splits the O2 into two oxygen atoms, and then because they're not stable when they're split, they'll connect to an O2. They're still not very stable, so that single is going to then attack our pathogens, and then now since that's happened, we're left with oxygen again. So the cycle just tends to go around. This O3 molecule is pretty unstable, and it generally lasts for about 8 to 20 minutes. So for disinfection, we want to aim for a 2 part per million ozone, and oxidation of iron is 0.44 parts per million per milligram of iron, and 0.88 parts per million per milligram of manganese. So that covers pretty much the disinfection stuff. Now I want to talk about some of the regulations that go along with the surface water treatment rule. And as we talked about our log treatment requirements with removal and activation, both of those combining to get our 4 log, our 3 log, and our 2 log. We've talked quite a bit about this stuff. In addition to that, we've got a residual requirement that we need to have 0.2 parts per million at the entry point to the distribution system, but we can't have over 4 parts. So it's important that we maintain within that. I would think that most systems would want to have considerably more than 0.2, but those are the minimum and the maximums. And then with our turbidity limits, we have a combined filter effluent less than 0.3 NTUs in at least 95% of the samples. And we have to collect those samples every 4 hours. We cannot exceed 1 NTU at any time. Sanitary surveys need to be conducted by their primacy agency every 3 years. It's one of the requirements. And there's a quick guide to the surface water treatment rule as well. So, on this table here, it shows us a few different things. It shows the maximum logs of credit that can be given for removal. So you can see when we were talking primarily about conventional and direct. So you can get less or greater than 2, 2.5 and 2 for Giardia, 2 for viruses, 1 for indirect. So you can see the conventional goes through that extra step of sedimentation, so it gets more removal. And then this just tells you how much is remaining, what we need to do to, as far as inactivation through disinfection to get to our required removal. All right. So in addition to that, we need to maintain certain disinfection residuals. So we need, this table shows us for small systems up to 3,300 population, the number of samples they need to collect each day. And they need to be collected at equal intervals throughout the day. So we have to ensure, this ensures that we've got a disinfection residual leaving the plant. So I want to talk to you briefly about a major thing that happened back in 1993, the Milwaukee Cryptosporidium outbreak. There was a time, it was in the spring, they had quite a bit of ice melt, they had some rain. The city of Milwaukee had 2 different wastewater, had 2 different drinking water plants. There was a failure at an upstream wastewater treatment plant, and it resulted in elevated levels of Cryptosporidium in Lake Michigan. And that's where these 2 water treatment plants got their water, was from Lake Michigan. So they had a northern plant and a southern plant, and each one of them served about 400,000 people. It turns out that there were Cryptosporidium cysts in elevated numbers, and they passed through the filters at the southern plant, and that caused 403 people to become ill, and 4,000 hospitalized, and 69 dead. So as you can imagine, this was a very, very big thing that happened in Milwaukee in 1993. And these cysts, we said, are small and they're not affected typically by chlorine. So how did they, what did they do to find out about this, and what did they do as a result of it? So didn't really know a lot until 1976 about Cryptosporidium. They didn't know the cause of the illnesses during this outbreak, but crypto has an incubation period of 7 to 10 days. And the problem with that is that if you test it, you're finding something that happened 7 or 10 days prior. So unfortunately, the mayor decided to issue a boil water notice. That was huge towards saving people's lives. In order to find it, the investigators examined ice that had been made during the outbreak, and they were able to find that crypto in the ice to confirm that that's what the problem was. So we said some of the key factors that caused this were excessive ice melt and precipitation. They had failures at that wastewater treatment plant. The water treatment plants had this practice of reusing their backwash water. And in fact, that was like concentrating these impurities, probably the crypto, so that backwash would come back into the front of the plant. So they kept pulling this back through. And then the turbidity limits, we'll see, were not adequate. They've changed considerably since this outbreak and as a result of this outbreak. So their turbidity measurements, they were normally below 0.25 NTUs, but they rose consistently to 0.45 NTUs during late March and April of 93. They had 2 spikes, a spike of 1.7 NTU on March 28th and 30th, 1.5 on April 5th, but they still didn't exceed that max turbidity limit at the time of 5 NTUs. So at the time of the outbreak, they had filtered water couldn't exceed a half an NTU in at least 95% of measurements each month, and they couldn't have they couldn't exceed 5 at any time. So throughout this whole thing, it didn't really appear as if they were out of compliance. And and this situation resulted it led to the long-term two enhanced surface water treatment rule of 2006. And this is similar to some of the things we've seen with changes to lead and copper rule as a result of what happened in Flint, or the changes to the revised total coliform rule, which resulted from an episode that happened in Walkerton, Ontario. So as you can see, we have the north plant was pretty stable and steady with the turbidities, and then the south plant had these couple of spikes. So let's cover the specifics on turbidity monitoring. So the limits are based off the combined filter effluent, and what type of filtration we're using. For conventional and direct filtration, these are our limits. So for combined, it must be less than or equal to 0.3 NTUs in at least 95% of samples taken each month. So at the time of the outbreak in Milwaukee, that number had been 0.5. So that's why they were they were over 0.3, but less than 0.5. Maximum turbidity of the combined filter effluent must not exceed 1 NTU at any time. And in 1993, that had been 5 NTUs. You must record the CFE every 4 hours, and the CFE turbidity meter must be located so the sample is representative. Typically, the best spot for that is usually near the inlet to the clear well. So we'll look at what are the turbidity monitoring requirements for individual filter effluents. They've got to be monitored continuously and re-recorded every 15 minutes. You don't have to report that data to the primacy agency, but you have to keep it on site and take any corrective actions that are necessary. Systems that only have 2 filters are allowed to do continuous monitoring, and they don't have to monitor each of the individual filter effluents separately, just at the combined. And once again, if we find issues, we need to take and do things to correct them. And the performance of the plan is how we operate is quite often dictated by these turbidity levels that we have. This shows a typical. It's good to show the treatment train and where sampling and stuff like that is done, our compliance points. So we've got a raw water source. We're going to have our raw water sampling location. We do TOC and crypto there. We add coagulant through flocculation and or sedimentation. We've got our filters. These would be these here green stars, or the individual filter effluent points, where we do that sampling for those. Here we've got our combined filter effluent turbidity monitoring location. We might add chlorine here before it goes through the clear well. This is where we collect our samples to determine what our login activation might be. We've got a storage tank that we could be using as well for CT, and then this is our sampling point for our entry point to the distribution system. So this just gives you an idea. It's good to see where all these things, how they all come into play. So next I'm going to talk about sanitary surveys. They're conducted by the primacy agency to identify potential risks, ensure that the system has the capacity and capability to provide safe drinking water. And they're an opportunity for the regulating agency to help the system along, provide technical assistance, education, things like that. You can expect that there's going to be an on-site inspection of the system, and a review of also the plans, budget, different things. And why does the primacy agency have to do that? It's covered under the surface water treatment rule for surface water plants and under the groundwater rule for groundwater plants. As we said, every 3 years for community systems, and then if you've got a non-community public water supply, they're only required to have them done every 5 years. There's 8 different elements of a sanitary survey, from compliance, operator compliance, source protection. We're covering treatment. There's also finished water storage, distribution, your pumping facility and controls, your monitoring, reporting, and verification of your data, along with how the system is managed and operated. What are they going to look at when they come out? Well, they're going to look at your individual and combined filter effluent turbidity monitoring records. They're going to look at your treatment train, your coagulation, flocculation, sedimentation, and filtration processes. They're going to look at what different chemicals you utilize, and are they NSF approved? You know, what are your dosages? How are you going about feeding them? What's the pump you're using? How do you store those chemicals? Are they properly stored? Your disinfection monitoring records and your log treatment records, they're going to look at those. What's the condition of the different components of the plant and the capacities of those components? Do you have an active cross-connection control program to avoid or to rule out backflows? You have backflow protection in place. What are your laboratory testing practices, and how do you, what's your process control to make sure that you're doing things, you're operating the plant properly? Are your operators certified? Do they have proper knowledge in how to operate the plant? Before the sanitary survey, you want to get together all your records. You want to make sure that they're available so that you can show them to the primacy agency. You'll want to expect to give them a tour of the plant, potentially the water system as a whole, out into the distribution system, including any pump stations or storage tanks. And then after the survey, you can expect that you're going to have a letter that comes back detailing any deficiencies and giving you the time that you have, identifying the time to correct those. There's 3 different types of deficiencies. Significant deficiencies are the most important ones, the ones that could cause public health issues. There's the moderate deficiencies. Those are usually not as serious, but if they're let go, they could cause problems. And then there's minor, which those are the less serious ones. They're still important to address, but it's usually more about just ideas on how to better operate the plant. Okay, so we have poll number 4. Which of the following is an accurate description of surface water treatment rule compliance requirements? A, turbidity must be equal to or lower than 1 NTU in 95% of samples. B, turbidity must be between 0.3 and 1 NTU in 95% of samples. C, turbidity must be equal to or lower than 0.3 NTUs in 95% of the samples. Or D, turbidity measurements are not required if inactivation exceeds 3 log. So I believe that is my last slide. How about we take 5 minutes? We set the timer for 5. We'll have our break. I'll come back on the other side and cover this poll. All right, well, thank you all. It looks like we've had almost 80% of the people have had a chance to look at the poll question and the poll, share the results with everybody. 64% of the people said turbidity must be equal to or lower than 0.3 NTU in 95% of samples. We also had 19% with B and 17% A, and nobody said that it wasn't required. So let's look at the answer is C. So the majority was correct. A is not, so it's 0.3 is, we need it to be less than 0.3, not 1 NTU. That's the one time has to be lower than 1 and adding 1 time. And then it's not the range between 0.3 and 1, it is actually less than 0.3. So if Greg is available, we will move on to his portion of the presentation.
Thank you, Daryl. I'm available in here. Thank you for that excellent presentation. Does it seem like my slides and audio are coming through okay, Daryl?
Yes, I can hear you.
Okay, great. Thank you, everyone. And I was taking note of some of the things that people are having difficulty with. We continue to improve these presentations, and you're actually helping. Some of the questions came in about, what's the demand in that particular. So I made a little note to change that question to say we're looking for the dose. That's what we were looking for. You will come across questions like that that aren't completely clear on certification exams. And also the question from yesterday, I had a couple typos that I'll just address real quick here. And then we're going to get into this topic of water treatment optimization, things we can do to modify the treatment process, and things we can do to ensure quality. Yesterday, there was a couple of things that I just wanted to address real quick. The aluminum sulfate, for some reason, there was a sodium in front of that, but aluminum sulfate, the symbol for aluminum is Al, so Al2SO4, SO4 is a sulfate. And when it reacts with water, if you remember, we were talking about it takes alkalinity from the water. And if you look at this equation here, you see the alum that's being added to the water. So for every one of those alums, there's 14 water molecules involved. And this 6HCO, that is the alkalinity that's being consumed from the water. So that alum is combining with the bicarbonate in the water to form this aluminum hydroxide. So you see that it's changed from alum to aluminum hydroxide, and that is a precipitate. It's a gelatinous flock that precipitates and goes down, and it settles through the water and collects in sweep flocculation. It collects the impurities in the water. And the second thing is I had a second typo, 2 typos yesterday, and we had this problem where it said it was supposed to say diameter of 65 feet, and it caused some problems for a lot of you because I was wondering what was taking so much time. And so the diameter, as we showed yesterday, uh, makes it one type of problem. And if we use circumference, it makes it another type of problem. So we were looking for the overflow rate in gallons per minute divided by square feet. Just a quick overview of that. We had the gallons given as gallons per day. So we had to divide by 1440 to get that in gallons per minute. Then we calculated the area, d squared times 0.785 with the diameter of 65 feet. Then we just, to calculate the area, then we just simply divided the flow in gallons per minute by the area to get 1.1. And the option the answer that you would have gotten if you had circumference would not have matched any of the options in the problem. So if we changed it to if it had a circumference, this is probably what many of you were doing. The flow conversion is the same. The flow doesn't change, but if we had circumference, you'd have to actually derive the diameter by dividing the circumference by 3.4, because pi times diameter is circumference. So we would have gotten 65 divided by 3.14 gives us a diameter of 20.7. And if we calculated the area using that number, you would have gotten a much smaller area. And if you take that that area, you take the flow divided by that area, you would get a very small area that would cause the overflow rate to be excessively large. And so if you did this equation yesterday and you ended up calculating 10.85, given the information that you had in the poll, that's probably what you would have gotten. So if that looks familiar to you as something you calculated and you couldn't figure out why does this not match any of the options, let me know in the chat and let me know if this little overview is helpful or if it's just more confusing. But the issue was that I allowed this this typo to slip into the poll. It was supposed to be diameter and not circumference. So you were presented with this kind of inexplicable problem yesterday. So now on to our topic for the ending part of this presentation. We're going to talk about treatment optimization a little bit. And optimization generally includes optimized goals that are beyond the requirements of the Safe Drinking Water Act. Daryl just got through talking about the requirements of try to be equal to or below 0.3 NTU. For optimized goals, a lot of plants are shooting for 0.1 NTU. And they're looking for optimized goals for disinfection byproducts. The regulatory limit for TTHMs, for example, is 80, but our optimized goal would be to try to get that below 60 parts per billion. And also there's some interim steps that we can look at. For example, if we take the turbidity in our sedimentation basin, the solids have settled to the bottom and our clarified water is on top. If we can get the turbidity at the sedimentation basin to be below 2, for example, that's another optimized goal. So that means we'd be taking the turbidity not just at the effluent, but midway through the process in the sedimentation basin. And so there's a lot more than this, but basically we're using some key performance indicators and some benchmarks to optimize our treatment process. And there's a couple of different optimization programs that you could lean on. AWWA has one, Partnership for Safe Drinking Water, and here is the AWOP. It's an association of state compliance primacy agencies, and here's an example of progress that actually has been made achieving optimized disinfection byproduct goals. And you can see the TTHMs here. You see that red line going across at the 60 mark. That's an optimized goal. The red line above it, the dotted line at 80, is the compliance limit. And so you can see in the first quarter through the of 2019 through the fourth quarter of 2020, a lot of these systems were still above that 60 mark, but they continued to make progress by looking at key performance indicators and making micro adjustments and maybe even some major adjustments. And they had some success getting their TTHMs below 60. And here is an example. This is a little bit different kind of a chart to read, but what we're looking at is the red line is the 95th percentile turbidity of all the plants in the program. And the blue line is the percent of measurements that meet 0.1 NTU. So this is an optimized turbidity goal of 0.1 NTU. And so more and more plants are meeting this goal. And you can see the red line is the turbidities, the 95th percentile turbidities. You can see it starts at over on the left-hand side, 0.27, which is just below the 0.3. And by the time we get over to the right-hand side, we see plants are hitting 0.11 and 0.1. Oh, so you can see the success of these programs, and you can access these here. I've included the links here. The US EPA has a drinking water optimization program. There's the AWWA Partnership for Safe Water. And then there's that Association of State Drinking Water Administrators. They call it the Area-Wide Optimization Program. So you can log into those, explore those sites, and take some of the KPIs that are being used. And here's an example, just zooming in on the reducing disinfection byproducts goal, the optimized goals for TTHMs, once again, less than 60, for haloacetic acids, less than 40. Those are the optimized goals here. And so some of the key components here are, first of all, enhancing the removal of the organics before disinfection. And to do that, one of the things you could measure is the levels of total organic carbon in the source water and in the treated water. And that could be a good performance indicator to let you know how well your process is removing small particles of organics, because carbon is the main component of all organic material. And also enhancing the disinfection process. So you could, some of those things that Daryl shared with us today, you could try to minimize the amount of chlorine actually used, and you could plan your disinfection points. One of the things that Daryl talked about was using ultraviolet light, for example, and things like that, like ultraviolet light, even though it might not have a residual, it could be part of the disinfection process and allow you to use actually less disinfectant. So you're optimizing the removal and the disinfection portion. So there's a two-tiered point there. And there's a great manual that you can download. I think Daryl has already mentioned it once, but the disinfection profiling and benchmarking manual by US EPA. That's a good document to have in your library. So we'll look at a couple of different strategies to improve removal here. And the first general strategy is monitoring the raw water turbidity. And it is going to help you to determine your removal efficiency. If the water coming in has, for example, a turbidity of 40 NTU, and the water going out has a turbidity of 0.2, you could use those two figures to see what your removal efficiency is. But also, as turbidity changes, you can see an image here on the right hand side of your screen of some mud or silt in the water, probably from a recent rain event. And when that hits a treatment plant, the turbidity is going to change radically, and therefore you probably have to change the dose of your coagulant. And so by monitoring that raw water turbidity, it can help you to stay ahead of the game. Now, I have 6 slides here that I didn't get to from yesterday, so these next 6 slides are not in day 2. But just talk about turbidity for a second. This is a good place to do it. Turbidity is actually a science where you shine light through a sample, and you can see that blue circle there in that image could represent a flow of water from the filters, or it could be a test tube that you insert in a handheld benchtop device. But a light source shines through the sample, and we actually measure the amount of light that's scattered at a 90 degrees from the light path. And so in this case, we see the light source is an LED, and then there's a detector that is some kind of a photo multiplier tube or some kind of a diode that measures the intensity of the light that's scattered and the intensity of the light that's flowing through. Often the EPA standards will mention tungsten filament lamps as meeting the EPA method requirement. And the tungsten filament lamps, they produce a spectrum that ranges all the way from infrared all the way to ultraviolet light, and it includes all the colors. And that's important because when we have particles of different colors, if you don't have a light that has all the wavelengths of those spectrums, it could actually miss some of those particles. But the tungsten filament, it has a good uh, spectrum. It includes all the colors, and it it's kind of it's just an incandescent type of a bulb. The tungsten filament heats up and produces this light. And there's the range of visible light there, what that I just circled. There's other sources here. There's laser diodes and infrared LEDs here that can also be used. These are becoming more popular for different applications. They last longer, but often if you use LEDs, you might have to use a combination of LEDs to make sure that none of the spectrums are missed. There also can be laser diode lights that can be used, and these LEDs and laser diodes are things that are more recent, and there's new sources of light that are being incorporated as meeting compliance requirements all the time. And so like I was saying, dual LED combines two types of LEDs, a white light and an infrared, and it can help you to correct for color problems or interference. The turbidity unit itself needs to be standardized and calibrated, and there's a chemical mixture called formazine that can be titered to represent a specific amount of turbidity. You can create a mixture that can be 2 NTUs or 10 NTUs or any level that you need to check, and then you can put that solution into your turbidimeter and calibrate it with it. And so there's a couple different chemicals, hydrazine sulfate and hexamethylene tetramine. That's a long word here. That's not something that slips off my tongue normally very easily, but those are actually mixed to create a turbidity standard. So turbidity is actually a superior way to measure solids. As you can see, it's an indirect measurement because you're looking at the amount of light that's reflected from a sample. However, the reason it's used is it's very sensitive to those very small colloidal particles. Whereas, as we discussed yesterday, that suspended solids test, it it can miss a lot of the particles that are in water. And of course, it would be uh, pretty time consuming and not very efficient to have to continually collect a total suspended solids test where a turbidimeter can run continuously. So you can get continuous measurement from turbidity, and it's going to detect those very small particles that would go through TSS filter that you wouldn't know about. Another important aspect of optimizing treatment is jar testing. And so basically in jar testing, we're simulating the steps of the treatment process. We're simulating three steps. We're simulating, first of all, the flash mix, the coagulation by adding the coagulant and mixing at a high speed. Then we simulate flocculation by mixing at a slower speed for a time. And then we allow the jars to settle just like sedimentation. And what we're looking for, each jar represents a different dosage. If we keep it real simple, let's say we had 6 jars and we had different dosages of alum. Let's say we had 5 milligrams per liter, 10 milligrams per liter, 15, 20, 25, 30, something like that. That would be a pretty wide range. We would go through the process and we would see which jar forms the best flock and the best settling and the clearest water, water with the lowest turbidity after it settles. And then after we get an idea, we might want to narrow the range of the dosages. So instead of going from 5 all the way to 30 or 35, maybe we found out that 10 was the best. So maybe we'd go from 7, 8, 9, 10, 11, 12, something like that. And we narrow in to try to get the best settling. And we want to, when we have changing water quality, source water quality, we want to jar test more often. And as we are looking at the changing source water, we can actually monitor at several points throughout our process. Obviously, we want to monitor the source water at the intake and possibly even upstream to know what's about to hit us. The settled water in the sedimentation basin, and of course, after each filter, and of course, the combined filter influent. We can also combine filter effluent. We can also combine these measurements by looking at the zeta potential, seeing what the overall charges are uh, in our coagulation flocculation process, conducting jar testing, and also we can make sure that we're monitoring and testing with a different range of pH, paying attention to the temperature and different ranges of alkalinity. So once again, you can see some different images here of source water quality changes. Here's that same image at the top middle of your screen. You see some runoff or rain has caused some upstream of this river, caused some sedimentation to enter the water. And you have some turbid water here at the bottom of your screen. It's churning up the silt and so forth. And that's going to have a lot higher turbidity if it hits the treatment plant. And so monitoring that source water turbidity, monitoring the settled water turbidity in the sedimentation basin, and of course the turbidity coming out of each filter are all good process control locations. So if we look at the settled water turbidity, we can measure at a certain frequency, and it's recommended to measure at each 4-hour period from each sedimentation basin. And the performance goal would be to get to less than 1 NTU 95% of the time when we have good raw water turbidity. If it's less than 10 NTU already, we would like to see a result of 1 NTU or less in the settled water. If the turbidity is greater than 10 NTU in the source water, we'd like to achieve less than 2 NTU 95% of the time in the sedimentation basin. So if we can get our settled water below 2 or below 1, you can imagine we're going to have a lot greater success when we get to our effluent. And we can improve jar testing over time by not only just looking at a range of coagulant dosages, but we can also look at our pH. We could adjust the pH up or down. We could look at the performance with some polymer addition, and we could also compare alternative coagulants uh, with our water, our raw water source. And we want to always make sure we are keeping track of all the water quality parameters such as temperature, alkalinity, pH, and uh, actual conditions in the source water and in the plant, such as flow rates. And there's a couple good links here to learn more about jar testing. And the jar testing made easy from the California Resources Control Board kind of walks you through an entire process, whereas the tech brief is kind of a quick overview, but both good resources. Another thing that you can do to improve settled water quality is to make sure you calibrate all of your chemical feed equipment. And you can actually purchase, this particular one, I think it's a USA Blue Book, but any of the major water suppliers would be able to provide a calibration tube for your chemical feed pump. And so you can see the lady on the bottom left of your screen. She is running a peristaltic pump. She has a feed tank on the left-hand side of your screen, and she has a calibration tube on the right-hand side of that image. And she's going to run it as close to the actual conditions as possible. So she has a tank there. That pump actually has to lift the fluid a little bit, uh, and it has some piping there so the restriction and the gravity lift is probably pretty close to the actual application in the treatment plant. And so using those calibration tools can really help. And considering also the use of a streaming current meter. A streaming current meter, it's a way to measure the overall charges. Remember, we talked about that yesterday. The coagulants usually have a positive charge, and the particles in the water, the contaminants, usually have a negative charge. So that the use of a streaming current meter is continually measuring the charge in the water just downstream of the coagulation point, of the coagulation rapid mix point. And to explore this topic a little bit more, there's a couple links here. Calibrating liquid feed pumps, there's a tech brief, and then chemical feed pumps and calibration from the Pennsylvania Department of Environmental Protection also has a good video on this topic. The streaming current meter, it's continuously monitoring the electrical charge in the water, and it's based on the balance of those positive coagulants and the negative particles. So being that it's continually monitoring that, it can give you a heads up real quickly if there's some kind of a change. If you get a lot more turbidity and it goes negative, it's going to warn you. If you have a lot less turbidity and now you have an overall positive charge, it'll let you know, hey, you have too much coagulant. And these things can actually be set up to automatically adjust the chemical feed. And that's what this image is showing us on the right-hand side of your screen here. The pump is being controlled based on the streaming current meter signal. So it's pacing it, has a 4 to 20 milliamp signal that's controlling that pump to dose more or dose less. But you have to keep an eye on this thing. You can't, if you use this kind of a setup, it can really be a benefit because it can adjust in real time quickly to a change in turbidity. But you have to ensure that you're overseeing what it's doing, and it takes a while to calibrate it. There is a article in this streaming current monitor used to optimize coagulant dosages. That first link there, waterworld.com. What that is, it's a little article that goes through one system's efforts, I guess I should say, to install a streaming current meter to do just this, what we're talking about, where it controls the chemical feed pump up or down based on the streaming current meter, and it goes through all kind of the challenges they had. It took them some some adjusting and some fooling around to get it right. But once they finally got it set, it was a success. It really helped them out. And then there's a second one by a vendor, Milton Roy, where it talks about the basics of streaming current detectors, and that's a good article as well. The flash mixing um, depends a lot on the mixing intensity. And if you have a mechanical mixer, like the image on the upper right, um, it's very important to make sure you have enough mixing intensity, and that is controlled by the pitch of the blade. And an engineering design team could help to ensure you have the right pitch. In other words, the angle, how intense is the mixing in one of those tanks. And generally with this kind of mixing, you're looking for the mixing to be completely mixed within 10 to 90 seconds. 90 is getting on the high end. You want it to happen as quickly as possible and as completely as possible, because all of your subsequent flock development depends on that having occurred. You want every particle to be in contact with the coagulant chemical early on, because you don't want microfloc developing way at the end of the process. You want it to develop right at the beginning, and then the flocculation is just growing those particles. With the other types of mixing, like the inline mixers and in the inline pumping mixers and static mixers, they can pretty dependably cause that coagulation time to happen very quickly. But if you have a mixing basin, you could have some challenge if you don't have sufficient mixing intensity. And there's some 10 state standards. I have the link here for you. The 10 state standards, they specify a mixing intensity, and the units they're using is 750 feet per second per foot. And you'd probably have an engineering team that would know how to apply that, because there's other factors to consider. The type of mixer that you're using, whether it's a paddle or a vertical mixer, the shape of your tank, the baffles, what kind of flows you're going to be dealing with. So there's other things involved, but just know that mixing intensity is very important if you have a mixing tank. And you can download those 10 state standards, and it does explain a little bit about the process and gives some standards about the speed of mixing devices. The average time for flocculation is around 30 minutes, and it could be more or less. But overall, the mixing tapers off. The mixing intensity tapers off as it goes through the process. So we looked at it yesterday. Higher intensity mixing at the beginning, and as the flock grows and it becomes larger, the mixing intensity tapers off. And there's a maximum flow velocity through the tank. You don't want it to flow too fast, between 0.5 and 1.5 feet per minute. So it's moving fairly slowly, a half a foot per minute. That's fairly slow. The water, you want to have plenty of time for flocculation to occur. And the peripheral speed, the tip speed of the paddles, so you'll see that mentioned in the 10 state standards as well. So that the outside edge of the paddles, it's going to be moving somewhere between 0.5 to 3 feet per second. So in 1001, the paddle has moved a half a foot. So that's the slow range, and the faster paddles near the front going about 3 feet per second. So that gives you the range of the mixing intensity for those paddles. And you don't want the flocculated water traveling to the settling basin to go too fast either. So in other words, once it exits the flocculation basin, you don't want to pump to take that water and just shoot it really fast into the sedimentation basin. That's all part of design, of course, and engineers would not do that anyway. But it's what we're dealing with, kind of sensitive, fragile flock. And we don't want to mix too fast, and we don't want to tear apart or shear the flock. Sure, there's another a sheep herder term, shear the flock. We don't want to cause shear forces to damage the flock by pumping it too fast. So that velocity between the flocculation basin and sedimentation basin between 0.5 and 1.5 feet per second. So it's going relatively slowly. And we want to make sure we have sufficient baffling. So we can evaluate the baffling between the flocculation cells. And we could even do that, explore it by looking at using dye and modeling the flows. And once again, here's a link to the 10 state standards for coagulation and flocculation. And then there's an article about the coagulation and flocculation process, about mixing. Now, those should be useful for you. For sedimentation basin, the equations we looked at yesterday are good to evaluate the performance of your sedimentation basin. If you're not getting those optimized turbidities, and you've optimized your coagulation and flocculation process, you have the right dose, you have the right mixing speeds in the coagulation and the flocculation, and you're still not getting good turbidity, you might want to look at what's going on with the sedimentation basin. Remember, the overflow rate is the flow divided by the area. The weir overflow rate is the flow divided by the feet of weir, and the detention time is the volume divided by the flow. It gives you a time in minutes. And you could evaluate these. It could be that your treatment plant continues to need to make more water as your community grows, and it could actually just outgrow the design specs of the sedimentation basin. So it would be good to look at these, or at least to know if you're nearing the upper limit of some of these. Remember, there was some suggested limits, the overflow rate somewhere between 1 and 1.4 gallons per minute per square foot, and the weir overflow rate, we didn't want it to be more than 20,000 gallons per day per foot of weir. And detention time, we're looking somewhere between 3 and 4 hours. Those are just general kind of almost rules of thumb. And you might even want a more optimized metric than that. But if you have some design metrics from when your plant was designed and what the engineers intended, you could compare the current performance to the design performance and see, is our sedimentation basin being overloaded. You also want to pay attention to baffling. You don't want currents you don't want velocity currents in the sedimentation basin. You want to make sure you're getting good sludge removal. You don't want your sludge removal equipment to wear out and you have some additional sludge that's not being properly removed, because that could affect your effluent turbidity. And then, of course, the influent and outfluent conditions have to be gentle. Influent has to be baffled and not causing any velocity currents, and the same with the outlet. The effluent channels have to create a very gentle flow so it doesn't disturb settling. Some modifications that can be added include some kind of a settler, tube or plate settlers. And you could also add baffling to help prevent flow currents. There's a couple of good articles here. One is on sedimentation and clarification from the state of Oregon. That's a good document. And then there's kind of a little blog here, and it's a vendor, but some of these vendor articles are actually pretty good. And this one here, they compared plate settlers and tube settlers, and they analyzed which is the best choice. And they came to some conclusions, and that might be something useful for you to check out. These settlers, the tube or the plate settlers, they kind of work the same way. A lot of people will explain it increases the surface area of the sedimentation basin. So, for example, the overflow rate, you notice you're taking the flow divided by the surface area. So they explain it like that. Uh, I I'm not sure that I understand that specifically, but the water is made to flow up through between these plates, and it still has a velocity that it's going from left to right, for example, and it tends to run into the plates, and the plates allow the water to flow upward, and the particles will slide back downward. And so these are called lamella plates. Here, they're usually at about a 45-degree angle, and the water flows up between the plates. And you can see the little circular image is kind of like a magnified image. You can see the water going up, and the particles they still have motion from left to right, and they run into the plate, and they're caused to settle. It interrupts their travel and causes them to settle faster. It decreases the time that they need to actually settle. So they're kind of physically prevented from going farther. If we look at it from another angle here, that dotted blue line represents the smallest particle that would settle in this tank. And it would be ideal if it had a little more time. So if you have the lamella plates installed in this tank number 2 where we installed the plates, you see the particle actually runs in, it physically hits the plate surface, and it begins to fall quicker. We've disrupted its velocity and its direction, and it begins to settle. Another way to improve settling in a sedimentation basin is to use ballasted flocculation. That means we're adding a weighting agent, and usually it's microsand. We're adding microsand along with a polymer usually just after we add the coagulant. And so the polymer, as you remember, it's a long-chained molecule that has different attachment sites, negative and positive, that allow the microfloc to attach, and it creates a larger and denser floc. And along with that, the microsand, it's a dense, small sand that's going to increase the weight and density of these particles. It would be like a diver putting on one of those belts, like a 50-pound belt, or like filled with like lead BBs, and it might be 50 pounds. You put it on, it allows you to go deeper, faster under the water. Same kind of a concept with the floc. So you can get a lot better removal. And here's a little bit of magnification here of some. You see the microsand itself on the left. That's what it looks like. But on the upper right-hand side of your screen, you can see some flocs being produced with microsand. I especially like that one on the far right because you can see the microsand in the middle, and the flocs with the polymer are attaching to it. And that's at a highly magnified level there. But basically, we're looking for a size of microsand. Generally, in the studies, there's lots of studies on this. generally between about 50 and 106 micrometers. It can range larger than that, but generally we're looking for that size, which seems to work best. And it has a specific weight that's 2.6 times heavier than water, and that's enough to help these flocks settle. The ballasted flocculation process, you can see there's the coagulation process, the rapid mixing, and then right after that, there's the flocculant, and the microsand is added just before the flocculation process, just before the flocculation mixing. And so that's part of growing the flock larger, the flock particles larger. So that high density weighting agent is added. The microsand is added along with the polymer in step 1, just after coagulation, and they settle to the bottom of the sedimentation basin much more effectively and faster. But then there's a third step. Generally, the microsand is removed along with the sludge. It's sent to a hydrocyclone separator, and the microsand is heavier and denser, and it's retained and it's sent back to the treatment process. So it's a circular process, and the sludge particles are sent to sludge handling. So you continue to use the microsand. To improve filter operation, a overall effluent goal would be to get filtered water turbidity down below 0.1 into U 95% of the time, not including that ripening period or that initial period just after a backwash. It would probably filter to waste or if until it gets below 0.3. And so instead of our maximum turbidity of 1, like in compliance, our optimized goal would be to never have a maximum turbidity over 0.3. And so that would be some optimized goals. And to attain this, we definitely want to ensure that all of the preceding steps are optimized. It wouldn't make sense to try to optimize a filter if our coagulation dosage and mixing, our flocculation mixing, and our sedimentation basin performance was not also optimized ahead of this. One of the things you can do is do a filter inspection. Here is a kind of an interesting picture here on the top right. There's a gentleman that is taking a core sample of the filter, and this is very similar to a sludge judge. It's a filter judge where he's pushing that tube into the filter while it's backwashing or lightly backwashing. If you can see the waste troughs, there's 2 troughs on top of that filter. You can see water flowing in those. That means the backwash is on to a certain extent, and the media is somewhat expanded. It might not be a full backwash, but that allows that sampler to go in there, and you can collect a sample of the media all the way down to the rock. And so what's the benefit of that? Well, in your sample, you can look at different things. One of the things you can look at is to look at the different media depths to make sure you haven't had any media loss. You can also look at the individual grains of media to see if they've reduced in size. Over time, media will wear out and its effective size will become too small. But some of the main things you would look at is there impurities being trapped in the filter? Is there mud balls that tell us that there's inadequate backwashing? If we have uneven media compaction, it could mean we have some underdrain issues like a broken underdrain. We could also observe the filter while it's backwashing for boils and dead spots. We might have some kind of a plug or a break in the underdrain. And we want to possibly collect some media samples to look at the size, if there's fouling of the media. And media will have to be replaced at some point. It might last 10 to 15 years. And there's a couple of good links here. There's a Texas has a good article on filter assessments, and there's also a good article on core sampling there that you could take a look at. So you want to also evaluate the filtration and backwash rates and compare them to design. And remember, it's the flow divided by the area, and you can compare those. And if you remember, if you have a too high or too low, it can cause problems. Um, if your filtration rate is too high, you might not be getting good filtration. A low backwash rate could allow for the accumulation of mud balls and contaminants. And if it's too high, you could lose media. You want to make sure that the media is expanding properly. And there's a couple of good articles here, optimizing backwash, filter self-assessment document that you can use, and then a video on how to perform a filter inspection. Those are a couple good links there. Using powdered activated carbon, it's often fed as a slurry prior to the coagulation flocculation process. And we're usually using it to get rid of taste and odor compounds, but it's also useful to get rid of organic compounds and even certain types of microcontaminants. And we're doing this before we even get to the coagulation process in an attempt to get rid of some of those taste and odor causing problems. Activated carbon has a lot of pores. It has miles and miles of pores in it, and it tends to absorb taste and odor compounds. It traps natural organic matter, and it can even trap PFAS chemicals, and of course VOCs and disinfection byproduct precursors. And the activated carbon can be in the form of powdered, which you would feed as a slurry, likely before coagulation flocculation, or you can use it as granular activated carbon in a filter at the end of the filtration process before disinfection to get rid of natural organic matter that could lead to disinfection byproducts. You can see here how it works. It has many pores, and the particulates just get caught in those pores. It also has adsorptive properties. And you can see a little image on the right-hand side. The bigger pores are capturing the large and small, and the smaller pores are capturing those very small particles. And it can be part of a media layer. So you see here we have a sand filter. It has sand, a granulated activated carbon layer, and then a sand layer again. The only drawback to this kind of arrangement is that the granular activated carbon media will probably have to be replaced before the sand, because the particulates will finally get loaded up in it and it can't be used anymore. This is a good solution for personal care products, pharmaceuticals and personal care products. They call PPCPs. And so we're going to do, I think this is our last poll here for today. And it's asking, what is the benefit of using activated carbon in water treatment? Okay, we're up to 82% here. And the majority of you have said all of the above. 71% have said all of the above. And that's true. Activated carbon does do all these things. It's one of the best available technologies for PFAS, and it removes the uh, natural organic matter, which is one of the main problems that causes disinfection byproducts. Today we covered, yesterday and today we covered a variety of topics. We covered water sources and quality, coagulation, flocculation, sedimentation, filtration, and turbidity. Daryl covered disinfection and water treatment regulation, and we just talked about some water treatment optimization ideas. We have some for our friends joining from Massachusetts. We have a link here for Massachusetts drinking water standard guidelines and the drinking water regulations for that state. And if you don't remember anything else, there's three points we might take away. Disinfection, which Daryl covered today. We talked about the inactivation of pathogens through a combination of concentration and contact time. We talked both yesterday and today about different types of removal processes, which include coagulation, flocculation, sedimentation, and filtration. We talked about optimizing these to remove those very small non-settable colloidal particles, which also naturally repel each other. And we also talked about compliance. Ensuring compliance with surface water treatment involves achieving the correct level of turbidity and also attaining the right treatment log levels through a combination of removal and inactivation with disinfection. And so I want to thank you today. If you want to share any thoughts that you had, we would love to hear them. Anything that you learned that was new, anything that you want to explore further, anything we can clarify. And if you learned something that you enjoyed learning about, you can let us know that as well. And if Daryl, if you'd like to come back on, we'll open up for questions here.
Here. Good job there, Greg. Thank you.
And just let everybody know, I put a link in the chat pod for the attendance self-certification and course evaluation survey. Again, please fill that out within 24 hours. And it's through filling that out and attending, that's how you'll receive your certificates.
I do see a question here, Daryl, in the Q&A. And Saudi says, I was wondering about removing microplastic from drinking water. We know that removing microplastics from surface water is a growing priority in water treatment due to their persistence and potential health impacts. Which technologies can be integrated into the water treatment train, along with where they can most effectively be inserted? Are there treatment plants that are designed to remove microplastics? And there are some articles on that, Saudi, that I was looking at. Let me, I'm gonna put this on presentation mode for a second. And see if I can find that. I don't have it right here.
Yeah. I guess my thoughts on it are is that as far as I know, there aren't any maximum contaminant levels that have been, created for it, and so, it's kind of a difficult one. You know, the motivation from a treatment plant to, take it out is typically driven by, you know, the fact that, the regulating agency is saying that it can't be there anymore, so, I personally don't know a great deal about, the treatments or if, you know, who's doing it. But, I think that if EPA came out with an MCL or some guidance on, or requirement that it be treated, then I think we'd see a lot more of that. You know, we've got a lot of these emerging contaminants that, are coming up, and I think that some of the stuff with like things like PFAS was difficult initially because there weren't any, contaminant level, requirements. And now that things are starting to head in that direction, it's provided for, an impetus for systems to start at least identifying it and hopefully treating for it.
I did find something, Daryl. It says, I just did a Google search, and it says that EPA does have a national strategy to prevent plastic pollution in the first place, but the treatment for it it's advanced. So they're looking at things like reverse osmosis, adsorption with activated carbon, and they're even using some biological treatment strategies. So it sounds like it's not only are you correct, Daryl, that there's no there's no MCL yet. It looks like it's it's fairly expensive when you start using reverse osmosis um, and things of that nature. That could get pretty expensive.
So it looks like we have another question. Do you foresee any issues with these treatment techniques when we start sampling PFAS? I have heard about ozone degrading PVC over time, wondering if that could create PFAS issues in 2027.
Hmm. I have not uh, heard the problem with ozone, um, but I would think that we would go by we would start first with the best available technologies that EPA is talking about, and they're using one of the main ones is activated carbon. Um, so that's what is the gist of the question in the end about? Is it about ozone, Daryl?
Uh, do you foresee any issues with these treatment techniques when you start sampling for PFAS?
The treatment techniques for PFAS?
I think just the techniques that we've talked about for surface water
Oh,
treatment.
oh, I see. Well, I think the only issue would be is if if there's PFAS in the source water, um, it it tends to require specialized removal processes. Um, and so you might have to modify your treatment process, but maybe I'm not understanding the question fully enough.
Well, I think that as we start sampling for it, we're gonna find it, and then, you know, are these treatment techniques gonna be sufficient? And I think that, you know, time will tell whether what we have is going to work, or if we're gonna have to add things to the treatment train. You know, a lot of it comes from, you know, the source water. My experience, quite often what ends up happening is it's just easier to change the source or to serve an area that's affected by PFAS from another area. I can think of a case where that happened in the Lower Peninsula of Michigan. So yeah, I think there's a lot to come out. PFAS has been an issue for for, I don't know, like 10 to 15 years since it's come up, but I think we got more questions than we have answers when it comes to it.
Yeah. Yeah. I'm still intrigued by the question though. I mean, uh, I, I think Courtney, you're a couple steps ahead of my thinking. But with the ozone degrading PVC, are you thinking that PVC in a component of the treatment plant, um, if it's like piping in the treatment plant, could be deteriorated and cause additional like microplastic issues or something like that? Well, if Courtney writes back, we can know more. But and I'm kind of, it seemed like a good complex question that I'm not sure if we're fully answering, but
Yeah, I mean, with the limited residual for ozone, you know, you would think that it's not going to get out into the distribution system, but
okay. Well, I'm going to hand it over to you and Scott. And I don't see any more questions right now. And I'll let you guys shut it down or make last call for questions. Thank you, everyone.
thanks, Greg. Great job.
Thanks, Greg. Yeah, we are a couple minutes over, but we'll hang out for a few more minutes if anybody has any questions. Again, reminder, scroll in the chat pod and click on that link for the attendance self-certification and course evaluation form and get that in within 24 hours. By filling out that form, and attending is how you'll receive your certificates. So we'll wait around for a few minutes. We've got a number of people that are logged off, but maybe somebody that's still on the line might still have a question. Okay, I don't see any more questions coming in. We've got a number more people who have logged off, so I think we're going to call it for today. Thank you again for attending, and keep an eye out on your emails for notifications for our other upcoming trainings. Thanks again.